Welcome to my third project for Apziva. This project was a really fun project to work on. It is about language processing and using learning to rank models. So, a little bit of background about this project. The client for this project is a technology company, and they are recruiters, and they are looking to create a learning to rank AI model pipeline for ranking candidates in their database for jobs that they are looking to fill. And so we had several goals in this project, and I'll just briefly go through those. We were first, our goal is to predict a candidate fit for a given keyword or job type, create an automatic ranking system. We want to be able to re-rank the list based on past hires, filter out irrelevant candidates from the list, and create a flexible cutoff in order to filter out those candidates. So a little quick EDA on the project just to get to know our data. It has the data that we were given for this project has 104 rows, 104 candidates, and 5 columns. It has an ID column that's an integer, a job title column, which is the job title of the current candidate in that row, their location, a connection feature, which is the amount of connections that they have on social media, and a fit feature. And so I did a little bit of searching around on the different features, and here we can see that the unique counts of the features and the missing values. So there are no missing values except for the fit feature. For every row, all 104 rows is missing a value, so we're going to need to create that. But the unique count was a little interesting. So we can see that for the job title, there are 52 unique job titles in a database of 104 candidates. So there's a lot of duplicate job titles in the database. So here's a quick look at some of the counts of unique titles, and we can see that some of them have up to about 7 copies of the same job title in 104 rows. So we have a fairly small data frame to work with, and a lot of the job titles that we're going to be working with are listed more than once for different candidates. Here's just a quick word cloud that we can kind of get a visual representation of what words we're going to see most in the job title feature. And obviously, human resources pops out, aspiring human resources professionals. So there's a lot of entries in our database here related to human resources. And there are some other entries related to other technical roles like computer programming and computer engineers and things of that nature. So little quick rundown of some of the methodology I used to tackle this project. I went through a data cleaning and transformation portion. I did some data augmentation in order to create some additional data to get a better idea of how my models are working, and we'll get a little more into that later. We created a supervisory signal, which is the keyword to search the database for. The keyword will be something like a job title that they are searching the database for. And then we're going to create a starred candidates history variable, and these are candidates that that have been starred for a specific keyword, and they are candidates that are either ideal candidates or candidates that were hired for that position in the past and are therefore somewhat of an ideal candidate for that position. I then went through a feature engineering portion of the project. We create some cosine similarities between the job titles and the keywords to create fit features. I created a custom feature called similarity to starred. So this is how similar the candidate's job title is to the starred candidate's job titles, and an is starred feature, which would be one for candidates that are starred for this keyword and 0 the candidates for not. Then I went through a model testing and evaluation portion where we test the models to see if starred or relevant candidates are listed near the top. Um, so a little bit about the data cleaning and transformation portion. The first section, the first thing I did was clean up the connection feature. This feature was actually listed as strings. So we changed all of the strings to ints, and there was a bunch of entries that said 500 plus. So I gave any entry with 500 plus a value of 600. And then I made a function to clean the location. So depending on what the user entered, I made some Python dictionaries to either change the language of their entry and print it out in English, or change the format of their entry into city, state, country where available, or state, country, or if they just put a country, then it will be just listed as country. Um, then I went and created some augmented data to help test this my learning to rank models a little bit better, since we had so many job titles in the data frame that are copies of each other. So to do this, I decided I was going to test with a keyword that's not really listed in the current data frame. And so I settled on the keyword zookeeper, and I added about 50 candidates into the database that have animal related job titles. Their job titles aren't exactly zookeeper, but they are closer to the zookeeper keyword than a human resources job title or like a computer engineer job title. And so you can just see some basic examples here. We have wildlife rehabilitator, exotic animal caretaker, primate specialist, wildlife researcher. And so for the keyword zookeeper, we're going to eventually expect these animal related candidates to filter above the HR candidates or the other technical candidates that are already listed in the data frame. For evaluating the model, I will expect that starred candidates will be on top. We will expect unstarred candidates, but having exact matches to the keyword, be directly underneath those. And then all of the related roles to zookeeper, but don't share the title zookeeper in the job title of the candidate, should then be related. And then after those, we should see all the unrelated roles. Here I am just creating the keyword zookeeper. We are creating the starred candidates history, so we can see the zookeeper has four IDs as values in the key zookeeper. So there were 4 people hired for this position previously, and these will be ideal candidates for the keyword zookeeper. To create the fit features, I went through 5 different types of models. We used TF-IDF, which is term frequency inverse document frequency, and it's kind of a simple statistical approach based on word frequency, and it uses exact matches of words and basically does some math and statistics to create a number that shows you how often this word appears. It gives you a good word count, but it doesn't. It's not able to pick up any semantic understanding or words that have related meanings but don't share the same word. We also used word2vec and fast text to generate word embeddings and cosine similarities. And we used global vector word representation, GLOVE model, and then we also used BERT, the bidirectional encoder representations from transformers model, which is probably the most powerful model and the best at picking out semantic similarities. So we use those models to create a cosine similarity, and to really understand what that means, we have to go over a little bit of what a word embedding is. So these models are created by training the models on uh, large amounts of text, like books or articles or websites, and they use those texts to create um, similar, like they put together similar words that are found near each other. So one of the common examples you read about is king and queen, and they're often mentioned together. And so the model is able to begin to understand that king and queen are often mentioned near each other in sentences and around the same subjects, and so they must have a somewhat similar meaning to each other. And after training on billions of words and billions of sentences, the model is able to begin to put together these relationships of words that have similar meanings. So what we do is we take these models and we create what are called embeddings. And embeddings are basically a series of numbers, and they come out as well, if you're using Python, they'll come out as a Python list of numbers. And we can think about these numbers as like um, coordinates in a multi-dimensional space. So, we think in 3 dimensions, but these models are actually multi-dimensional, and they come out with an embedding of a word or a phrase with many different numbers. And we can think about those numbers as coordinates landing that word or phrase somewhere in this multi-dimensional space. So words that have similar meanings will land in similar areas of this multi-dimensional space. And so here we can see in this picture an example of the word developer and the word engineer. And if we get the cosine similarity, what we're actually doing is getting this the angle from the origin of the multidimensional space to where these words land in the multidimensional space. And if the cosine similarity is close to 1, we know that they are landing in a very similar place. This angle, the angle is telling us that both of these words, in this instance, developer and engineer, are landing in the same area. If it's closer to 0, they're unrelated, and if it's closer to -1, then they have opposite meanings. So here's an example, kind of a pseudocode in Python of how I got the code embeddings for TF-IDF, Word2Vec, fast text, global vectors, and BERT models. And basically, we just iterate through the job title feature. We get embeddings of the candidate's job title. We get an embedding of the keyword. In this case, I was using the keyword zookeeper. We get the cosine similarity, and then we assign that similarity to the fit value. And in this way, I created a fit TF-IDF, a fit Word2Vec, fit fast text, and fit global vector, and fit BERT feature. And I added all of those features into a data frame called DF combined, along with all of the other original features from the original data frame. So after that, I created a custom feature called similarity to starred. And so for this feature, I basically got all of the IDs for a given keyword. And then we iterate through those starred IDs for the keyword, and we make a list of all of the embeddings of their job titles. And then we actually get the mean embedding of all those job titles. So we kind of get the average of all of the ideal embeddings for this job title. And then we can get the cosine similarity between a candidate's job title and the similarity to starred ideal mean of ideal job titles. And then I also created an is-starred feature, which is helpful for a lot of the models we're training downstream. Is starred is one if the candidate is a starred candidate for this keyword, and zero if it's not a starred candidate for the keyword. Keyword. We created a few different ways to test the model, and we basically tested three different kinds of models. There's a pointwise model, a pairwise model, and a listwise model. And then we had some sort of hybrid approaches, which we will get into when we get into the specifics of the models. I also tried a sort of heuristic semantic approach, which is basically just a geometric mean of similarity to starred and the fit BERT value. And we'll see later on that it actually did fairly well compared to a lot of the trained models that I tried. So the first model that I tried was just a regression approach. And this we used a random forest regressor, and we used FitBERT as the target, and we used all of the other features, all of the other fit features we created, plus the connection feature and the similarity to starred feature. And then I tested a pointwise with continuous prediction approach. And here we used all of the fit features, but we used the is starred, so 1 for starred, 0 for not starred as the target variable. And we used a random forest regressor to try to get prediction values for each candidate. And then I tried a pointwise with categorical approach. So that uses the same, all of the features and the is starred feature, but this time we used a random forest classifier and used the predict probability function to predict the probability that this given candidate is a starred candidate. And then I did some what I was calling soft target regression. So here I created a target that was it's basically it's one if the candidate is starred, and if it's not starred, it's going to be the fit BERT value plus the similarity to starred value divided by 2. So the average of fit BERT plus similarity to starred. And then I used a random forest regressor. And I also tried another approach to this soft target regression. And this approach was interesting. Let's see here. So this creates a fit target variable. It sets starred to 1 and the rest are just going to be fit BERT values. Then I tried the light GBM lambda rank model, and we used an NDCG optimization. Here you can see all the parameters. I'm not going to go through all of these and explain them all, but they're basically the default parameters for this model. And we created a prediction feature using this light GBM lambda rank. I did XGB lambda mart, and I used the objective pairwise, the objective NDCG, and the mean average precision, the map objective. And so we created 3 different models with those objectives in this loop here to test those. And then I did the XGB lambda mart with a pairwise and NDCG objective, and I used a hybrid target where we set fit BERT values to different levels from 0, 1, 2, 3, and 4 using 5 quartiles to kind of test what would happen if we broke the target into 5 quartiles and then ran a prediction to see if each candidate was a starred candidate. And then I attempted a RankNet pairwise ranking model with a neural network. And so here's the code that I used to do that. And I'm not going to go through this whole code. It would take too much time, and this video is already 20 minutes long. So um, if you're interested in how that works, you can dive into the GitHub. And we also did a lambda rank listwise neural net here with a is starred target. Um, and this code is also fairly long, so I'm not going to get into each line of how this code worked. Um, for the evaluation, we created a few different evaluation metrics. There's precision at K. So if we're looking for starred candidates to be at top and there are 4 starred candidates, we will expect the best model to rank the top 4 places as the 4 starred candidates. We created a mean rank of starred candidates evaluation test. So what is the average rank of the starred candidates? If they're supposed to be in the top 4 positions, we would expect the average rank to be 2, I guess. And then the mean reciprocal rank. So this is kind of a test showing how high is the top starred candidate for a ranking model. And then we have the normalized discounted cumulative gain, which considers both rank and relevance of candidates, and it kind of rewards models that rank candidates higher, and it penalizes ones that push them down further. And so it kind of balances the overall ranking quality and the precision of the rank of the model. And so here's a quick look at the evaluate ranking function that I created. And so we can pass it candidates, and we can see where those candidates land in terms of where we expect them to land at the top of the list. And so here's a quick look at some of the top ranking models for the word zookeeper. And I kind of ran a loop through the data frame, and first I tested for the starred candidates to see how well they performed and if they landed on top. And then I removed those star candidates, and then I tested for the candidates that have exact matches to the starred candidates but were not starred in the database, and we would expect those to then be on top if we remove the starred candidates. And then I removed those exact matches, and then I tested for all of the related matches. So for the candidate, for the keyword zookeeper, we will expect all of the animal related job titles to then be next, and then followed by HR and technical roles on the bottom of the list. And so running through this loop with the different models, we can test the different features that we created from the models, and we can see that some of them actually did very, very well, and some of them did very, very poorly. And so it was interesting to see which ones did well and which ones did poor. The soft regression target did quite well for the zookeeper keyword, and some of the neural nets did quite well as well. My geometric mean fit BERT FESR did quite well. So this is not actually a trained model. It was more of a calculation between the similarity to starred feature and the fit BERT feature, and it actually fared quite well with the keyword zookeeper. I then went and decided to retest the data frame that has all of my additional data that I added into it with the keyword aspiring human resources, and then retested all the models, reran all of the whole notebook. And so I tested for the starred candidates for the aspiring human resources keyword, and then I removed those starred candidates again, and then I tested for all of the job titles that have human resources, HR, or human or resources in the job title, and that was able to give me an idea of the related keywords, and if they were putting human resources job titles above all of the others. And we can see that some of the models did quite well again. The FESR, the geometric mean, the non-model feature did quite well. The soft target 1 did quite well, soft target 2 did quite well. Some of them were sort of in the middle. Um, the Lambda Mart pairwise hybrid target did well. What else did well? RankNet pairwise neural net did well. And so here I just kind of go through which models did well with both and which didn't. But we kind of, at the end, I kind of came to the conclusion that uh, that the the pointwise continuous model with the soft target regression features were some of the best models for both keywords, and also the RankNet pairwise neural net did quite well for both of the keywords. And then surprisingly, the third runner-up, the non-model heuristic calculation of the geometric mean between the Fitbit value and the similarity to start feature actually fared quite well. And that was quite interesting to me that that I was able to create that without using a trained model. And so this feature, could be a good feature to use. It's highly interpretable. It's effective and it doesn't require any training. So it might require a little bit of additional testing to make sure that it's working, but it was interesting to see that that worked. I did some experiments with trying to figure out cutoffs, what values we could use to cut a list off, but that proved to be a little bit difficult to determine, and I eventually figured out that to really determine accurate cutoffs, we would need a really big data frame and a lot of testing in order to start to hone in on values of cutoff values that would allow us to cut out unrelated job titles and always leave in related job titles without cutting out people that might be fits or leaving in people that are not fits into the list. So that's something that would require a lot more testing and a lot bigger of a data frame and more time. So yeah, in conclusion, the pointwise continuous soft target regression models were quite good. The RankNet pairwise neural net was very good, and the Fitbit FESR geometric mean calculation also fared quite quite well. In the future, I was thinking about this project, and I think it could be a good idea to add some cosine similarities for sections of actual resumes. So if we could get actual resumes for different candidates and resumes of starred candidates, we could then compare different sections of the resumes to each other and maybe get an even better idea of how related or how good of a fit a specific candidate is if we have a more rich set of data that you might find in a resume as opposed to just using the job titles and the starred candidates job titles. Additionally, comparing to starred candidates, if there is some bias in the hiring process, then we're kind of carrying over that bias into the models if we're comparing to starred candidates. So we could think about getting together with HR department and maybe a diversity, equity, and inclusion professional and creating an ideal resume. And instead of using starred candidates, we could compare candidates in the database to, the ideal candidate, and make an effort to create cosine similarities between an ideal candidate and not candidates that were perhaps hired with some human bias, if we believe that there's some kind of human bias in the hiring process. So that was a real quick rundown. I tried to make it fast. Looks like it's just over 30 minutes, but that was a real quick rundown of this project. If I wanted to go into detail, I could probably talk about this for a couple hours, and so I'm not going to put you through that. But if you're interested to learn more about this project, you can check it out. There's a link to the GitHub down below, and you're always free to message me and say hello on LinkedIn. I'd love to hear from you, or get together and work on some kind of this project or anything related. So again, thanks for listening, and I will see you at the next Apziva project.